Welcome to the class of intelligent product design. Now, in this very final phase, as promised, we will be discussing about some of the case studies. This case studies has not been taken from outside, but from inside some of the alive projects that we have carried out in the SMSS lab of IIT Kanpur, so that you can get the first hand information about such systems, and you can get inspirations on designing different types of intelligent products on your own. So, in the first phase, I will talk about two such products. Both the products we have been able to develop due to the sponsorship of Portscape. So, we must acknowledge Portscape for their sponsorship through the CSR activity to develop such products. The first product is design and development of a miniature rotary actuator, which is based on shape memory alloy wire. It is called Flexinol SMA. Now, this particular product, how is it helpful for the mankind? Well, it is something that can be used for medical robots, because as you know that in a robotic, let us say if you are carrying out some surgery like a medical surgery with the help of robots, it is very difficult to use motors in such situations which are electromagnetic in nature, and also you need to develop such kind of robotic systems in a very small area and in a very high precision way. All these things can be done with the help of shape memory alloy wires, just like the muscle based system which I am going to show you. Another point is that, of course, shape memory alloy can be used in terms of expanding or contracting a system, because it is a smart material, but they generally cannot produce rotation, but they can only produce translation. So, in this particular development of a product, we have been able to develop a rotary actuation using shape memory alloy wire. So, let us see how this intelligent product has been developed. In the first phase, we will talk about how this shape memory alloy can be developed first to create a linear actuator. Then from there, we will go to the rotary actuation part. Now, I need to say you something about this smart material called shape memory alloy, right. So, this material belongs to the group of smart materials in a way that they respond to a change of thermal field around them, and because of this thermal field their structure, the crystal structure changes. The crystal structure changes how? It goes from martensite to austenite crystal structure. So, as you can see in this particular case, that for this type of a system we can have in the room temperature this kind of a martensite crystal structure, and as you increase the temperature it goes to austenite phase and it goes to this kind of a crystal structure. Now, then martensite to austenite, it actually contracts. So, that is very interesting, isn't it, that generally everything expands as you apply temperature, but in this case this structure, because of the phase transformation from one crystal structure to the other, it actually contracts. And as it's a large contraction, and if you try to stop the contraction, then it applies force, because it wants to contract and you try to stop it, naturally it applies force on the system. Now, if I try to cool this from the austenite phase back, then you are going to get this structure back, which is also known as the twinned phase of martensite. And then if you, in this phase it is very flexible. So, modulus of elasticity is quite low, and then if you apply force, you can actually deform it to a very large extent, so that you can go to detwined phase. Once again, if you apply temperature, it goes back to the austenite phase. If you look at this kind of a system, if I try to use it in a comparison of weight versus the power, then you would see power means power to weight ratio, then you would see that it beats almost all the conventional motors, DC motors, pneumatic actuators or hydraulic actuators, because it has a much higher power to weight ratio. So, the choice of the smart material is this first step for developing the intelligent product. The second important thing is that now we will go to the nature inspiration. Okay, that is what I talked in the last class. Okay, we start to think of it that what are the cases where in a very small space nature has been able to develop large forces. Okay, some examples are there in the nature in terms of the crab's claws, because crab's claws are confined in a small space muscles that can generate a large space. Some examples are there in our body itself. If you look at these muscles in our body, both of them are cases where the muscular fibers are not along the direction of contraction, but they are arranged at an angle to the direction of contraction, and this angle is something that we are going to call as the pennation angle. So, by taking inspiration from nature, we can actually develop pinnated muscular architecture using shape memory alloy wear. So, this is a bipennate muscle architecture. This details of it we have published in a Nature scientific report paper, but here I just want to show you the concept of this bipennate muscle architecture. But in the left side, as you can see, is the actual architecture that is used by nature, and in the right side you can see what we have developed using SMA based architecture. So, what we have done is that we have figured out that corresponding to our requirement of force and deformation, what is the best pennation angle, because if the pennation angle is, let us say, 90 degree or close to 90 degree, then you will not be able to get a large deformation out of the system. On the other hand, if it is close to 0 degree, you will get a large deformation, but you will not get a large force. So, you have to have a kind of a optimal angle in which you can get a reasonably good force and a reasonably good deformation out of the system. And also you need to think of it how to fast contract it, but that part I will not cover right now. So, now you see here that we put the SMA wires in a bipennate system and then we apply voltage to it, and you can see the force that we are being able to generate in a simple planar architecture. Like on our left we have these planar architectures of SMA based bipennate actuator, and even there we have been able to generate forces like 100 close to 100 Newton of force that you can generate. And you can also see what will be the corresponding the temperature that you have to generate with the help of the Joule effect or with the help of the current. So, the particular system here actually it looks like this, and the colors actually shows that how it is heated and as captured by an IR camera. So, you can see it here that if I arrange it in a 3-dimensional system, not a 2D, then how the SMA wire is empowering a bipennate architecture. Okay. So, this is, and you can see here that how these bipennate architectures are getting contracted around this region. If you look at it, and you will be able to see it. So, the video will repeat and you look at this architecture very carefully, and you will see that how this deformation is going to happen in the system. So, I will just run this system once more and you should be able to see it, that you can see now the SMA where it is in a 3-dimensional system, and you can also see where the force is getting applied, and now the area that I have marked for you, you look at it how the contraction is happening in this particular area. Okay. So, and then you can also see that how that force is utilized in order to drive a linear actuator, and this force is much higher because this is a 3-dimensional system. This force is close to 200 Newton. So, that is the advantage of using a double layered system. Now, we will come to the rotary actuator part of it, that how we can develop rotational movement out of these linear actuators. And here you remember the egg analogy, very similar to that. You can see that this bridge type system has been developed. Then there are other systems also which are mechanism based. We have talked about different mechanisms. So, you can see the mechanism based systems, and this rhombus type system is also something which is close to the amplified piezo actuators. Okay. So, in all these systems, if you can have this linear actuator, that linear actuator can create a much larger transverse deformation of the system. So, that will be the core, the compliant mechanism in order to generate the rotational motion in the system. Now, first you have to have the core, which is a compliant mechanism, and you can see here that the rhombus structure we have finally selected, and we have done an analysis using COMSOL, and you can see how the SMA wear is contracted, and because of that the large deformation is getting produced in the transverse direction. As I have told you, amplification factor is about 4, which is very high. Now, once we are confident about it, now we create this architecture all around a rotational system, which will be actually rotated with the help of a cam follower mechanism. So, the SMA architecture is now all over, and you can see it from different perspectives. With this SMA arrangement, now you can see that the compliant mechanism is in the core, which I have told you earlier, and now you can see that as the compliant mechanism is working, and you can see how this rotation is happening on the cam system, right. So, that is the way you can actually use a kind of a linear actuation and transform the linear motion to the rotational motion. So, that is what we have done in this particular system. Now, we have developed different prototypes. In some prototype, the envelope dimension is more, and it can create a torque of 5 Newton meter. In some prototypes, the beta prototype, the envelope dimension is smaller, but the torque there is also less, about 1 Newton meter. Depending on different applications, you can actually have different types of designs for such a system. Now, this development of SMA based healthcare system is the final product. So, we need to benchmark for any such products, you need to benchmark it against an actual product. So, Portscape has a linear stepper motor model 20 DMK, and then if you compare that model, you can see that output force is 30 Newton and maximum stroke is 15 millimeter, and this SMA actuator has been able to create a force of 150 Newton and a displacement or stroke which is much larger, 20 millimeter. So, that means in the benchmark test we have successfully passed in terms of developing the product. So, our research has a lot of impacts where you can actually go through each one of these and to get a better idea of the system, but here we are focusing on the case studies. So, now I come to the another part. This is also another CSR project sponsored by Portscape, and this is design and development of an adaptive smart stick for sit to stand motion. Now, many times the actuators will be the same, but the product will be different. So, using the same strategy you can develop many different type of intelligent products. So, in this case the actuation capability could be very similar, but the product that we will be developing is for a different application, which is for sit to stand motion. So, let us start to think of that, what is the sit to stand motion? The elderly people, they need actually support as they want to stand from their sitting posture, or if they want to sit from their standing posture, because every time there is a change of the center of gravity that is happening to the system. Now, that also will be beneficial if the stick itself changes its height as they are trying to move up or down. So, you need a linear actuation system. Now, for such smart sticks, the self weight of the system is about 1.6 kg currently. Of course, the constant drive is how to make it lighter and lighter. So, you can think of using Trees principle to make it lighter. Okay. Maximum height change, that is 90 centimeter, this part, the height of this whole thing, and the range of motion where the stick change should happen is about 15 centimeter. Maximum uplifting force, that is the force support that you will need, is about 130 Newton, and weight limit for the person who will be using it is about 120 kg. So, 130 Newton is almost equivalent to about 13 kg of force. So, you can see that you can support a considerable significant part of the weight through this system. So, our target of course is to reduce the self weight by 40%, and also our target is how to use the actuation in terms of reinforcement learning, which is how to make this actuation system more intelligent. And what are the sensors or the embedded systems that you have in your possession? In this case, we had the pressure sensors, the onboard IMUs, and we have a lot of physiological data like the pulse and SpO2s, etc. So, the methodology is in terms of first of all getting data from the sensors, that is sitting, stand to sit while climbing stairs or abnormal walking in uneven floors and slopes, and the sit to stand while descending or while actually sitting on some place. Okay. So, based on all these things, we first have to start to collect the data, because we have to create an kind of an intelligent system. Now, you see, we started the design and the prototyping part of it. In the prototyping part, you have to first make a functional model of the system which will display your concept. So, you do not have to think too much about the specifications. Broadly, you have to obey it, but not like the exact specifications. And the aesthetic design also is not thought at this particular point. At this point, another thing that is needed is in terms of user experience or discussion with the user about your product. That will give you many new inputs. For example, we thought of developing the smart stick which can only change its height, but then the user started giving us new inputs like can we have a flashlight system so that in the darkness we will be able to utilize the stick. Can we have a on off switch so that we can trigger it whenever it is required? Can we have a SOS switch so that if the person feels that he is not well, he is about to fall, the SOS switch can be triggered? Can there be a buzzer alarm? That means if the person has already fallen down, then this buzzer alarm will be there so that people in the neighborhood will know that the fall has occurred. And the health status through the oximeter and pulse display and the red blinking light. So, these are all systems that we have later on added to the basic module based on the user feedback to our system. Now, I told you that we need to get a lot of data in terms of the ground reaction force data collection. Okay. So, how do we do it? Of course, we need transducers which will be sensing that what is the force, reactive force that is coming from the floor or from the area in which the person is walking, and then we need to design a microcontroller. Initially, it was based on Arduino, and later on, because there will be lot of heavy loads on the system. So, we started to use the Raspberry Pi based microprocessor, and then we started to take the online data collection, inferencing from the data collection about the range of force, the accuracy of the force, etc. And the onboard power supply also is needed in terms of running the system, onboard analog to digital converter in order to get the data, and flex sensor amplification system we have to incorporate. So, all these things once you do, then you can secure a good force data collection. You can see that the PCB that has been designed specifically. So, first of all we develop the architecture, and then we have to design the PCB in terms of customizing the system for these very specific applications. So, you will not get such PCBs in the market. That means, your project, based on your project, based on your demand of the project, you have to actually develop your own PCBs for the particular application. But this PCBs will be always based on either microcontrollers like Arduino or based on microprocessors like Raspberry Pi. So, that is important to choose that whether you will go for a microcontroller or a microprocessor. And as I told in the last class, that this will all depend on that how much generic you want to make a system. For example, if our intention was only to sense the data and trigger the movement of the actuator, then a microcontroller like Arduino would have been good enough. But because we wanted to also implement the artificial intelligence through reinforcement learning, that different surfaces give different types of reactive force. So, we needed to have much more processing capability of the data. And the reinforcement learning, how it helps us? Well, reinforcement learning, the detail of it I have not covered in this course, which soon I will be covering in a more advanced course, but part of it you can also see in my course on cognitive robotics. This is mostly based on the kind of decisions that you are giving to a system, that whether a particular system is the design is actually progressive or regressive. That means whether you are getting the desired output. In such a case, you give a positive incentive to the design. If it is regressive, you give a negative incentive. And through that learning process, the system automatically sets the gains so that it gets customized for the person. Now, you can see the prototype and understanding the things. So, Raspberry Pi, as I told you, learns through the data from the IMU sensor. IMU sensors are inertial sensors, so that they can give you data like acceleration, okay, and generally they can give you data in all the 6 axes. That means you can get 3 translation data, so acceleration along the 3 directions, as well as 3 rotational data. So, you can compile all these data together from the IMU sensor. And then we have Arduino that can take data from the force sensor. So, you can use both Arduino and IMU. Now, this Arduino can directly control some of the things which are like a good example of edge computing, that you do not bring it to Raspberry Pi. For example, the indicators, the buttons, okay, this type of small things Arduino can directly take care of. But for the bigger things like the learning part, etc., you need a Raspberry Pi. The Raspberry Pi can also instruct the Arduino. That means they can crosstalk with each other. So, that is the final system, and you can see how the raw data is collected from the accelerometer, gyroscope and force sensing data. So, that is from the IMU sensor, the gyroscope in terms of collecting once again the similar type of angular velocity and angular acceleration data, and the force sensing data. So, from this data you can actually get the kind of a similar to what we call a gait pattern, that the walking pattern, that when the force is maximum, when the acceleration is maximum, and how it is changing in all the directions. And then you can use it for the learning part of the exercise. So, you can see here all the 3 accelerations, and you can see all the 3 angular rotation data in the gyros, and then you can see the 2 forces in the curves, which can be used for the learning part of the system. So, now you have to develop a neural network, okay, and you have to use a learning system. In this case, we have used a LSTM system, which is a recurrent network to adaptively control the actuation of the stick. So, in the learning phase, you need to develop the neural architecture, and that can be based on the number of hidden layers that you are going to choose, and the weights that you will be giving to this connectivity between input to the hidden layer and the connectivity between hidden layer to the output. Okay? And these weights can be adaptively varied with the help of the LSTM. So, where you are getting the data, you need some classifier from the data, which will classify the necessity of the requirement of the stick at different conditions. Okay? So, when for example, a person is working on a particular type of condition, soil condition, okay, the data will be accordingly changed, and then when a person is attempting to sit or stand. So, the variation of force at different stages of the experiment is recorded, and then we have used something which is very common for feature extraction, is called support vector machine in terms of extracting it. So, that displays a fairly good amount of accuracy, though not very high, about 85% accuracy. Now, I also told you that one of the intentions is in terms of mechanically making it very lightweight. In order to do that, we have used carbon fiber tubes, so that the overall weight gets reduced, and the carbon fibers, you know that it has a high strength to weight ratio. So, its strength is 2.5 to 5 gigapascal, modulus of elasticity is 200 to 500 GPa, and the weight on the other hand, the density is a little above than the density of water, something like 1200 to 1400 kg per meter cube. So, it is very lightweight yet strong and stiff. So, this kind of carbon fiber use system, we have used it in terms of developing a hollow cylinder out of it, and that substantially reduces the weight of the system. As of now, the actuator part of it, which is a standard linear actuator, is the heaviest element. So, that has to be balanced by reducing the structural weight of the system. Another interesting thing that we have been able to incorporate is also inspired from nature, and that is these four appendix at the end of the stick. These parts are based on auxetic materials. Now, the two advantage that you can get through the auxetic materials, number one is that it has a negative Poisson's ratio. So, it can take the shape or the unevenness of the surface, so that it gives maximum surface area. That means, it can give maximum gripping, and that helps the elderly people in terms of supporting their weight. So, that is one advantage. The other advantage is that they can also produce a large amount of structural damping. So, that means, if there is a shock while putting these stick, every time the elderly person is moving the stick, they are lifting and then putting it. So, the shock that is coming will not be transferred to the handle. So, the handle is safe, because this works also like a shock absorber, and this curve is showing that a large amount of shock absorption is possible from such a system. So, I think this is all in terms of development of the two products, intelligent products, one in terms of developing a product that can be used as a motor for medical robots, and that can understand based on the requirement or different types of environmental condition what is the torque requirement, and we can keep it compact inside a smaller area, and the smart material particularly gives you a very large power to weight ratio. And in the second case, I have not of course shown the use of the smart material, but we have a design where shape memory alloy is used instead of a linear actuator. But in the second case, the design of the meta structure to absorb the shock and the intelligence in terms of understanding different types of surface patterns and different types of customer requirement in terms of the support forces, the intelligence has been provided to the system with the help of the reinforcement learning, LSTM based reinforcement learning, and thus we have been able to make the system intelligent. So, both are examples of embedded system which has been made intelligent either through the soft intelligence or through the physical intelligence. Thank you.